Welcome to the demonstration of HE Node B local gateway solution. Tata Elxsi LT's solution includes HE Node B running on a Freescale platform, UE running on a KVM and TI platform, EPC emulator which is running on a desktop. As a part of release 10 feature, TEL provide a solution for local gateway. The feature of local gateway includes local IP access and optimized handover. Due to the limitations of bandwidth and network capacity, there is a tremendous strain on the network operator to provide the service for the ever increasing customers. To handle this scenario, the operator must offload the data traffic from the cellular network to the fixed line broadband network when the users are inside buildings. This traffic offload for a cellular network can be done by the feature called LIPA, which is nothing but the local breakout. If the home eNode B supports local IP access, and once the user camped on the home eNode B, then the user can access its local network as well as EPC core network at the same time. So, this shows the setup diagram for local breakout. It includes UE which is running on a KVM platform, home eNode B which is running on a Freescale platform, L gateway which is running on a desktop which has a connection to the local network such as file server, printer and internet, EPC network which is also running on a desktop which have a connection to the external network. As per 3GPP standard, in order to achieve a local breakout, UE must first attach to the EPC network which is achieved by attach procedure. So, in order to achieve this local breakout, UE should connect to the LIPA PDN which have a support for local IP access. For any data which is arriving at L gateway, the L gateway has an intelligence to route the packet to the core network or a local network based on the data services. For example, when UE want to communicate with the printer, it will route the data to home eNode B and home eNode B will route the data to L gateway. So, L gateway will decide based on the data service, it will decide whether it has to go to the local network or it has to go to the EPC network. Since it is a printer, it will route the packet via local network. Now, we can see the demonstration of our first scenario which is nothing but the local breakout. So, our demonstration includes UE which is running on a KVM platform, eNode B which is running on a Freescale platform, the corresponding RRHR here which is connected via RF cable, and we have a L gateway which is running on a desktop PC, and we have a EPC emulator which is also running on the desktop PC. Now, we can have a closer look at our hardware. So, this is our eNode B hardware. Here we have a commodulity board with 8156 processor and P2020, and we have a FPGA card, and this is our UE hardware. Here we have a commodulity with TA processor, and this is a KVM L2 L3 board. We can start our execution procedure. Now, all the hardwares are up and all the entities like EPC, L gateway are ready and running. First, we can configure and initialize the eNode B. Then we are configuring L gateway. Now, eNode B, L gateway are configured. Now, we have to sync up with the UE. So, we need to initialize and configure the UE. So, now we can run the UE script for configuring the UE. So, now UE got synced up. Now, we can start with network attach. So, we can see in the MME log, attach got completed and we got initial counter setup response. Now, we can start the data transfer. Now, UE got attached to the EPC network. In order to achieve a local breakout, UE should establish a PDN connection which should support the local IP access. So, that we are achieving using PDN connection request. So, from the MME log, it is observed that a PDN connection has been established. Now, we can start with the data transfer. To make sure the data is going via stack, we are creating an ARP entry. For example, here we are creating an IP address of this PC where we are running a UL LIPA server, and we are giving a MAC address of UE ETH1. So, the data will go via UE ETH1 and it will reach the corresponding server. So, we are starting our IPUF client. So, now we have started IPUF server on that PC. Now, we can able to see data received on the UL IPUF server. And also, we can confirm from the L gateway log that data is going via L gateway. Similarly, we have started DL LIPA client and server. DL LIPA server and DL LIPA client, and also we have simultaneously we are running UL LIPA server and UL LIPA client. From the L gateway logs, it's verified that both the data are going via L gateway. Similarly, we can start EPC data transfer. So already we have started LIPA, UL and DL. Now we have started EPC core network data transfer. So from the log it is confirmed that the L gateway routes the EPC data to the EPC network, and the UL data which needs to send to the LIPA PDN, the L gateway routes the data to the LIPA PDN, and for DL the L gateway route the packet to the HE node B. The next important feature of L gateway is handover optimization. The reason for handover optimization is to reduce the HO signaling at core network when more users are connected at the core network. As per 3GPP standard, during S1 handover, MME will act as an entity which will communicate with the source eNode B and target eNode B. As part of handover optimization, L gateway will act as an entity which will communicate with the source eNode B and target eNode B, so that we can avoid the HO signaling at the core network. This shows the setup diagram for handover optimization. It includes UE, which is running on a KVM platform, source eNode B and target eNode B, which is running on a Freescale platform, L gateway, which is running on a desktop PC, EPC emulator, which is also running on a desktop PC. When a handover gets triggered, the source eNode B will send handover required message to L gateway. So the L gateway will, based on the configuration parameter, L gateway will decide whether it has to go for an optimized handover or a non-optimized handover. In case of optimized handover, L gateway will prepare a handover request message and it send it to the target eNode B. Similarly, all the handover messages will go via L gateway. Once a handover is completed, L gateway will intimate the EPC emulator about the switching of the UE. Similarly, in case of non-optimized handover, L gateway will act as a proxy and it will send the handover required message to EPC emulator, and EPC emulator will prepare a handover request message and it send it to the target eNode B. Next we can see the second demonstration of our second scenario, which is nothing but a handover optimization. So demonstration includes source eNode B, target eNode B, UE. Similarly, we have other entities like L gateway and EPC, which is running on a desktop PC. The corresponding RRH is here. This is the target eNode B connected with RF cable. This is source eNode B RRH connected with RF cable. Similarly, we have a UE RRH. Which is also connected with RF cable. Okay, now target eNode B is up and everything is running. UE has already attached to the EPC core network, and also we are connected with a LIPA PDN. So now we are going to try with a handover optimization. So for that, first we need to configure the optimized mode using CLI. We are doing the configuration for optimized mode. In L gateway, the handover mode is set to optimized. So now we can trigger the handover. So now HO has been triggered. From the log, it's confirmed that once a handover required message reaches at L gateway is preparing handover request message and it's sending it to a target eNode B. Similarly, other handover messages are prepared at L gateway and sending it to target eNode B. Finally, L gateway is indicating to MME through a path switch request message. UE has been switched to a new target eNode B. Also, we could see the data transfer is running through a target eNode B.